And we're going to take a look at section 3.8, exclusive OR function. My tablet died completely this morning, so I need to get off my backside and actually install the software and everything for the new tablet I got. I got it, I received it. I just have been putting off getting it all installed. So hopefully I don't have to do any writing, because that may not go well. Once we get through this section, we're to the point where we look at the programming side. Um, so we'll get away from the writing for a while anyway, at least for probably a week. I think we'll get there today, but we'll see. I have model sim up and running myself. Okay, exclusive OR function. It's denoted by this symbol, plus with a circle around it. And the resulting value of it is this right here. So you got X and not Y, or not X and Y. So that accomplishes the same task as these. Exclusive OR is equal to 1 if and only if X is equal to 1, or if and only if Y is equal to 1. Let me demonstrate that with Excel. Okay, so we can have 0, 0, 1, 1. Here we can have 0, 1, 0, 1. Not X would be the complement of X, which would be 1, 1, 0, 0. And not Y would be 1, 0, 1, 0. And then X and not Y. Again, that and you treat like multiplication. So we're going to take X times not Y. And X or not X and Y. So we're going to have not X, which is this one, times Y, which is that one. Let's see if I did this one right. A2 times D2 X, not Y. Okay. And then this, which is X and not Y, or not X and Y, also known as X, and then X or Y. Again, we treat it like addition with one exception. So this plus this. Our one exception is 1 plus 1 is equal to 1, but I don't see that issue here. So this is what they're trying to indicate to you in the book when they say that. When they say is equal to 1 if and only if Y is equal to 1, but not when both are equal to 1 or when both are equal to 0, and then the X also. So if you look over here, if one of them is equal to 1, then it's 1. So that's the only time it gives you 1. If they're both the same, both zeros or both ones, that gives you 0. Does that make sense of what the XOR does? Okay. Doesn't explain why we're even studying it, but that's how it works. They give you different identities, apply to that. You got 0, then that just gives you original X. Okay, makes sense. Here's that first one. X can be anything. That's what that's saying. So X can be anything, and then the next one's 0. Well, if we got that, we got this one, there, and we got this one and this one. Because the next one's 0. And then if I look at the result of that, which is over here, you see how the original X doesn't change. It stays 0 and 1. So the zeros in the Y doesn't actually do anything. Now our next one is we got X and then the 1 there. That would be this one, this one, this one, and this one. And you notice here's X, 0, and the XOR becomes a 1. And then the X is 1, XOR becomes 0. So it's complement. And that's what's saying that X XOR 1 is equal to not X. Grab a drink here. The third one, that's X XOR X is equal to 0. Well, in this case, I know this is labeled as Y, but X XOR X means that they're the same. So that. So you notice when they're the same, that gives you 0. And that's where that third one's coming from. Now these are fairly easy to see just from looking at the truth table. And X XOR not X, that means they're different. If X is 1, this will be 0. So if I look at where they're different, when these values are different, you see it's always equal to 1, which is what they're saying in that fourth one there. That one's probably not so simple to see from a truth table. We could build it. That's equal to the complement of X. Okay. So complement of that is going to equal 1, 0, 0, 1. So then, if I look at X and not, or X XOR not Y. X, which would be these, and not Y, which would be these. You have to translate this. See, this is 0 and 1. Well, if I went back to 0 and 1, right here in A3 and B3. 0 and 1 gives me 1. The complement of that is 0. I wrap my mind around that. I meant to, I won't waste time to build all the columns. But if I build all the columns, we'd see that that's true. I'm not going to be able to see this last one from the tables or columns I have. Okay, any of these data has been proven with the truth table, like we indicated. Also, been shown that exclusive OR is both commutative and associative. Commutative means you can flip them around. A and B, you can put B and A. For the associative, see how we have the parentheses around A XOR B? You can change it, put parentheses around the B XOR C, or not have any parentheses at all. So it means the two inputs to an exclusive OR can be interchanged without affecting the operation. It means that we can evaluate a 3-variable exclusive OR operation in any order. For this reason, 3 or more variables can be expressed without parentheses. This would imply the possibility of using the exclusive OR gates with 3 or more inputs. Okay. However, multiple input exclusive OR gates are difficult to fabricate with hardware. In fact, usually a 2 input function is usually constructed with other types of gates. Let's talk about this up here. That to satisfy this x XOR y here, try it again. To satisfy this x XOR y here, we can use this setup. So we can use these ands and this or with these inverters. Now to do it with Nand gates, then we accomplish this using this setup here. Looks like we got 4 Nand gates. So there's only a limited number of Boolean functions can be expressed in terms of, oh, by the way, where they're getting that from is if you look at this right here, x not y, or x and not y. So x coming in here, not y is coming in here. And here's our and. And then there's not x and y. So for this one, the not x is coming down here, and y is coming in there. So that's our and. And then the plus in between them, they're both coming into an OR gate. And that gives you that right there. Okay, so this is coming in as x, this is coming in y. We've got our inverter in the front. So x, y. I don't see where they list that at all. See if I can draw that one. Just curious. Oh, they're talking about it here. The x, y, and then the complement of that. That's this x coming in here, and that's that y coming in here. And then the circle in the front inverts it. And then they tell us that that's equal to not x or not y, which matches this one right here. And then that's, you can think of it as being multiplied times this x right here. That's and. So this is coming out here, and here's my x coming straight into this, and that's where the and is for that. But it's inverted again. I see these, I see these. I don't think they don't show all the steps, but I think that this and this work together to give us the. See, they're coming in. Both of these are coming in. That's like this x times y here, x and y. And then there's an inverter there. And we said we can rewrite that as not x or not y, which means I should be able to take this and do the complement of it, and take this and do the complement of it. But I'm not seeing where they're doing that. I'm probably just missing something on that. But I'll trust them. I'll believe him. Okay, exclusive war operation, or wait a minute. Important piece somewhere here. Okay, here it is. While a limited number of Boolean functions can be expressed in terms of exclusive or, nevertheless, the function emerges quite often during the design of digital systems. It's particularly useful in arithmetic operations, error detection, and correction circuits. That's why we're covering it. It seems like why do you do it? Since looking up here, you can rewrite it in terms of all these other ones, and that's usually the preferred way. Okay, exclusive OR operation, 3 or more variables can be converted into ordinary Boolean function by replacing the XOR symbol with the equivalent Boolean expression. The equivalent Boolean expression, remember, was over here. So this is what it gives you. Boolean expression clearly indicates 3 variable exclusive OR function is equal to 1 if only if one variable is equal to 1, or if all 3 variables are equal to 1. I guess that makes sense when I think about it. Because if you had your X, Y, and Z, actually they use A, B's, and C's. Okay. A, B, C. Put C over here. If I had A, XOR B, remember the only time it's equal to 1 is if just exactly one of them is equal to 1. There, like that. Now C was 0, 0, 1, 1. Then what I just did, A XOR B, and then XOR C, it's equal to 1 if exactly one of them is 1. It would look like that. So then if I look at my original, A, okay, so those would be my ones. And I'm indicating that it's equal to 1 if only one of the variables is equal to 1, or if all the variables are equal to 1. So if I look at this, I got 0, 0, 0, that's equal to 0. 0, 1, 0, here I got one of them equal to 1. That gives me a 1. Here I got 1, 0, 1, 1. Two of them are equal to 1, so that's 0. But down here, all three of them, 1, 1, 1, gives me 1. So that's what they're indicating. It says, in the case of three or more variables, the requirement is that an odd number of variables be equal to 1. As a consequence, the multiple variable exclusive OR operation is defined as an odd function. Boolean function derived from the three variable exclusive OR operation is expressed as a logical sum of four minterms whose binary numerical values are 0, 0, 1, 0, 1, 0, 1, 0, 0, and 1, 1, 1. Again, the trick there is there's an odd number of ones. 1, 1, 1, and then there's 3. This is binary numbers are meaning four minterms are included in the function, and they have an even number of ones in a binary in general in. So this is for 3. We got our 0, 0, 1, 0, 1, 0. We got our 1, 0, 0, and then we got our 1, 1, 1. So those are ones with the odd number of ones. Our even function, though, on the other hand, here we have 0, 0, 0. So there's 0 ones. Here I got 0, 1, 1, so it's 2 ones. This one I got 1, 0, 1, so it's 2 ones. And this one I got 1, 1, 0, so it's 2 ones. So that shows you picture-wise what's happening with the odd or even function. I have these back in chapter 2, the end of chapter 2. There it is. This is on page 68. And they show you the symbol here. That's our symbol for the exclusive XOR. So you have what looks like an OR, and then you got that line going through like that at a curve. So this is what that's saying. You got your XORs here, and we can do A XOR B first, and take the result of that and combine it with C, and that gives us our 3-input odd function. Here you do A XOR B, take that result, put it with C, you do the XOR there, and then you invert it. That inversion right there comes from this right here. You notice this is A XOR B XOR C. This is A XOR B XOR C, but then there's a prime on there, which inverts it. And so that's why the inversion's on the very front. Have another drink. 16 minterms for 4 variable Boolean function. Half minterms have binary numerical values with odd number of ones. The other half have an even number of ones. That just kind of makes sense when you think about it. Okay, parity generation checking. Exclusive OR functions are very useful in systems requiring error detection and correction codes. As discussed in section 1.7, a parity bit is used for the purpose of detecting errors during the transmission of binary information. A parity bit is an extra bit included with a binary message to make the number of ones either odd or even. The message, including the parity bit, is transmitted and then looks at the receiving end for errors. And this just shows what we talked about up here. That doesn't really have anything to do with the parity checking. But they're just showing you have an odd number, 0001, so there's 11, 001011, and somewhere in here, there's 3. I guess right here, 3 of them. 1110, that's where you put a 1. Now, on the other hand, if you got an even number, like this one right here, this is 1111, so there's an even number of ones. Here's our even parity generator truth table. Okay, so we just got our standard setup for the X, Y, and Z. And okay, just double checking all of them. It says even. Notice that there's no ones here, so there's an even number of ones. Here we got 1 and 1, so we got an even number. We got 2 of them. Here we got 1 and 1, 2 of them, 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 and then 1 and 1 and 1, we got 4 ones. So that's their even. And by putting the parity bit on there, that ensures that we got an even number of ones. And again, when you think this, think voltage going through a line of some sort, and it's recording how many are coming through at this level to be qualified as a 1. Okay, an error is checked if is detected if the checked parity does not correspond with one transmitted. Circuit that generates a parity bit and transmitter is called a parity generator. The circuit that checks the parity in the receiver is called a parity checker. Nothing exciting there. It's just talking about what happens, as the 4 bits received have an odd number of ones, so it generates an error. Here they're getting 4 inputs, and it's an even parity checker, so we need to have an even number of ones. No ones at all, so that's even. 1 and 1, that's even. Down here we got 1, 0, 1, 1, and then a 1 over here. There's 4 ones. So again, it's putting the extra parity check in there to make sure it's even. Now, what I've never read, I've read about this parity checking and so forth, is that that's really fine, but then like what happens if 2 or 3 of these are messed up? And it could be that that doesn't occur very often, so it's never really discussed. And that's the end of 3.8. Questions, Aida? Okay. Yeah, they don't really go into much detail of. If they went into much detail, I probably wouldn't understand. They're just saying this happens, but they don't describe it from the engineering standpoint of, well, how does it happen, type of deal. Well, section 3.9 gets into the hardware description languages. It says manual methods for determining logic circuits are feasible only where circuits are small, like the very simple examples we've looked at. For anything else, a practical circuit, designers use computer-based design tools to reduce costs and minimize the risk of creating a flawed design. When they say reduce costs, some of these packages are expensive, but they have optimization modules in them, and so that you can optimize it and get a simplified circuit. So you don't have to sit there with tons of paper and mapping and using those identities, postulates, theorems, and so forth back on chapter 1 or 2, wherever it was. And you can still come up with the same design. Prototype integrated circuits are too expensive and time consuming to build, so all modern design tools rely on a hardware description language to describe, design, and test circuit and software before it's ever manufactured. And it's really not like the language you might think of. It's not like your standard programming language and so forth. It's not a markup language, but it's just kind of its own type of language. Hardware description language, HDL, is a computer-based language that describes the hardware in textual form. Before the advent of HDLs, designers relied on schematics of block diagrams and logic gates to represent and specify a circuit. That methodology is prone to error and its results are costly to edit, especially for complex circuits. In contrast, today's HDL-based design tools create an HDL description and then derive a schematic automatically and correctly as a byproduct of the design methodology. Revisions of the HDL description simply simplify the creation and revisions of a schematic. This is what I was talking about. The HDL is a modeling language, not a computational language. HDL resembles an ordinary computer programming language such as C, but is specifically oriented to describing hardware structures and their behavior. We're using a model simulator. Logic simulation displays the behavior of a digital system through the use of a computer. Simulator interprets HDL description and either produces readable output, such as a time order sequence of input and output signal values, or displays a waveform of the signals. The simulation of a circuit shows how the hardware will behave before it's actually fabricated. Simulation detects functional errors in design without having to physically create and operate the circuit. Errors are detected during a simulation and can be corrected by modifying the appropriate HDL statements. A lot of areas in when you're manufacturing, whether it's electronics or anything, that's costly. So if you don't have a design tool up front that allows you to find your errors before you start consuming material, then that really puts you at a disadvantage. I had a friend that ran a machine shop up in Wichita, and he would do special orders for one of the aircraft companies. He's no longer in business, but and he said it would be costly because they'd be asking him for something new. And since they've never done it before, they would come up with a design as well as they could, and then they would go out and they would cut the part. And well, when they cut it, they realized that it just didn't work, and so all that material and time was lost. So it's costly. So when you have a tool that help reduce that, then it just works out better. He told me numbers, and I can't really remember what the numbers were, but some of them get pretty expensive when you get rid of all the material. You think a machine shop would just be like pieces of sheet metal, wouldn't cost that much, but there's a lot of different types. Okay. Test functionality design is called a test bench. That is to simulate a digital system. The design is first described in HDL and then verified by simulating design and checking it with a test bench, which is also written in the HDL. Now, one thing I haven't figured out is how to write code for the test bench. There's a lot I haven't figured out, but that's the main one in Model Sim. If you got over here, okay, there it is. So we got this. We looked at last time. Got two inputs. Remember we compile selected. Comes back, tells us it was successful. That's weird. Why did it throw clear up there? Okay, go to my library. Right click on that, simulate. Oh, let me show you it from scratch. Okay, so I'm gonna go ahead and close that. Maybe. I don't see it close, so I guess I just do a new project. So file, new project. Oh, simulation's running. That's why it wouldn't let me. Simulate. Simulation. Okay. So you do a file, new project. Okay. Didn't I quit it? Yeah, I quit it right down here. Maybe I was going too fast for it. One more time. File new project. Close that. Yes. Okay, so newest project. Give it some kind of name. Point it to a project location if you need to. This just leave as is. Now click OK. Now when it pops up with this, you want to do a create new file. Give it some kind of name. And I think we're choosing Verilog. Although you can do other languages as you see. And then click OK. Now when that's done, you click this X to close this window. And if you double click testing.v here, it opens it up. Now here's where you write your program. Actually, let me program the XOR since we're on that. Let's finish that section. And I'm looking at on page 115. And again, if our goal is to implement the XOR without using any XOR components, then I want to use the how do you do a comment? Do it that way. The book says X and not Y, or not X and Y. Okay, so we're going to have two inputs. So I guess I'll say X and Y. We're going to have one output, and I'll just go ahead and leave it as out. So I'm going to have X, and there's an and there, and not Y. And I think it's tilde Y. And then the OR, which is two pipe symbols, and then not X, so tilde X and Y. Save that. Let me right click on this and choose compile. Compile selected and see if I got any errors. I do got an error. Unexpected XOR. That means that my name of it probably can't be XOR. Can. So I gave you that worked? You're right. That did work. That's bizarre. Here I use lowercase, but there doesn't allow lowercase, which means XOR is probably a reserved word if I had to guess. Okay. So if I do out2, assign out2 equals to X, XOR Y. Sure enough, turned red, didn't it? Okay, so save that. Compile selected, make sure I don't get any errors. I do got an error. Here. I don't know. That's probably where the error is, though. So let's see if I put, let's try that first. X XOR. Comma shouldn't need. Then again, I'm not an expert at Verilog. Near XOR syntax error, unexpected XOR. So I don't think it likes the XOR, does it? Sure looks like a reserved word. It's putting it in red. Mind you, we wouldn't want to do it anyway because they tell us that we would prefer to write it in these terms. Hmm. Bitwise XOR. Hmm. Not that I fully expected them to give me any kind of nice examples, but oh well. I got out two. That's not giving me an error, but it's not really necessary there, is it? Okay, so then if I I'll go to my library, expand this work, and what one did I just create? This one here. So right click on that and simulate. Now I want my wave window to be open, so that there. Now the X here, I can right click on it and choose force. If I'm in the right place. So I have to drop it over here and then force it. Okay, let's try it here. Right click there. There it is. Force. Okay, put a 1 there and put a 0 here. So I'm right clicking on that. Now if I run the simulation, that should give me a 1 because only one of them is a 1. Right up there. See where my mouse is circling? How did I zoom that by accident? Well, just bouncing back and forth your nose. I don't know. Let me start that over. In simulation. Oh, is it? Uh, share your screen. That'll give me a break from what I've done wrong with my Zoom window there. That it's a very user-friendly package. Oh, sure enough. Well, it doesn't come back. You have to terminate it and then start it over. Yeah, when it's doing that, there's no way to get it to get it back. Okay. Yeah, let me simulate this. Go to my wave window. Okay, drop my X and Y on there. And my out. Right click on that, choose force. Put one in. Right click on this one, choose force and put 0 in. Now if I run my simulation, I see what it's done. I just don't know how I did it. I got it running for a total of 0 nanoseconds. That's put 100 there. There, that's better. I have no clue how I did that. I didn't even notice changing that to 0. This is how long you can run your simulation. So there might be other ones where it makes more sense to run them for 500. Do you need a code back so you can copy that? Okay. There you go. Okay. Do you have a semicolon after your input here, Pierre? Let's see. Go ahead and share your screen again. Oh, can't have a comma after the num2. I think I have a semicolon, don't I? Let me look. No, I do have a comma. Never mind. Semicolon, assign out equals x and y, or that looks right. Go ahead and right click on testing.v and compile it. Actually down. Yeah, right there. Just right click on that and choose compile. Compile selected. You shouldn't need num. You shouldn't need the num2 though. If you could delete num2 and the comma, and I'm guessing it'll still work fine. No, you do need the num1 because that's going to be our. Oh, wait a minute. Output is out. What did I have over mine? Oh no, I had out. Yeah, that num1 should be out. I'm shocked that didn't give you an error. Then you go to the library, the tab down. I don't think you saved it. Go back and save it, and then do it and compile again. Because I've made that mistake over and over. I would click over in the code window on your right hand side, and then click the little diskette. I'm not even sure where the save is for the individual file. The diskette, the floppy diskette in the upper left hand corner. Okay, now compile it. Then you can right click on that to simulate it. I don't see a wave window. I'm just missing it. So maybe probably under the view, if I had to guess, or window, one of the two. Wave. Yeah, there's wave down there. Now you can drag the X, Y, and out over and that. And then you can right click on the X and choose force. Correct. Yeah, get rid of the hertz on there and so forth. Just replace that value with 1. Click OK. And then force Y to be 0. The run is, you see where it says 100 NS? The first button to the right of that one right there, that's the run. It's not very obvious. Yeah, there you go. You're at the same place I am then. Okay. Okay, so go back to my wave here. And if I put my mouse over it, looks like it pops up and tells us 1. And this one's 0. And this one's should be 1. Why can't I get my mouse on that? That's 1. I think the H stands for hex, but I'm not sure about that. And that's what it should give us. Since one of them is exactly 1, then that should give us that. If I right-click on Y now and choose force and change it to a 1, click OK, and I run my simulation again, we should get 0 for the out. Maybe. If I'm interpreting that right. Okay. Boy, I must be losing it. Okay, set it to 1. H0. Well, what was I looking at the first time? Yeah, it is putting out 0, isn't it? Well, that's on the Y. Okay, I'm going to have to zoom in. Let's see. Last time I did that, I screwed it up. So let me zoom in. There's the out, and it's giving us a 1. Here's the Y, and it's giving us a 0. One. Let me do it another way. So come down here. I'm going to force Y to be 1, and run. Okay, so that's 1, 1, 0. Okay. You know that force, I just seem to have more trouble with it. This is what I was talking about, this code down here. I copied this from above because it tells you what it's running. And then I forced it to be 0. Or forced it to be 1, sorry. It's the first number that's Now what there should be somewhere in here is some way to build a script. Compile all, compile arrange, compile. I never saw anything last year either. But you can type in the commands directly down here. I wonder if I could put them with a comma between them or a semicolon. Run. Of course, I wasn't watching it. Okay, so let's do that again. You do your up arrow, brings up a previous command. Okay. Looks like you can put semicolons between them. So that might be, if you have to use that, a little bit easier way. So that would be our Y. And this would be our X. So here, if I set the X, I set that equal to 0. Then if I set the Y equal to 0, that should give us 0. Does that make sense what I'm doing there? Correct. I mean, that makes sense copying the code and editing it that way? Okay, so if I do a control, the what? No, you can't think of it from a standard language. It's yeah, it's more of a design type language. It's like where you're forcing the voltage to be low, so it's 0 on the X and the Y input, and then you're running the simulation to see what your output's going to give you. So here, this is our, what is that? That's our X. So X is 0. This one is our Y, which is 0. And it returns us 0 there. If I do an up arrow, again, if exactly one of them is a 1, like that right there, that should give us a 1 when I run it. So this one is 1. This one looks like a 0. And that gives us a 1. Question is, how do I clear that? Break. I could stop the simulation and restart it. That would clear it, the wave file. Okay. And again, see, the command it did was restart -F. So you should be able to put these in some kind of file and run it. Other. The do probably makes more sense. Okay, so save that. Macro files. Run it. Oh well, I won't waste time on that. But anyway, that's how you type it in. So if your force doesn't work, which sometimes I have trouble getting that force to work, then you can do it in that manner. Back to this. This talks about the keywords that we have, except for that's froze. I don't know why that freezes. Yeah, I'll have you write a program in it. Okay. We got module, we got in module, input output, wire. We'll talk about wire later on, and or not. So those are keywords you can use. For emphasis, clarity. Lines of text terminated with a semicolon, and any text in between two forward slashes, and the end of the line is interpreted as a comment. So again, the slash uses a comment. Comment has no effect, just as you might expect. Blank spaces are ignored, but they may not appear within a text of a keyword. That makes sense. Verilog is case sensitive, which you'd expect. Module is a fundamental descriptive design unit in the Verilog language and is declared by the keyword module. It must always be terminated by the keyword in module. Okay, so we got our module name here, our beginning parentheses, closing parentheses with a semicolon here. That ends that statement. And we declare output, and we declare input. So however many inputs you have, you put here, and however many outputs you have, you put here. True power of this is if we had not that you'd ever have anything that's complex, but A, B, C, D, E. You had 5 inputs coming in. And you had some kind of weird combination here. A and not B or C or C or not D, and D and E. What that little blue that means? That's the fact I'm still running my simulation. Simulate in simulation. Do I quit simulation? Yes. Oh, that's nice. Didn't keep any of what I. Oh, it is good. Okay, so save that. Right click on here and choose compile. Compile selected. Compiled it. Now, how long would it take you to build a truth table with five inputs? quite a while, wouldn't it? And there would be actually 32 rows in it. So it'd take you a long time to come up with this. Let's see. Let me right click on this. Compile selected. Go to my library. Right click on that, choose simulate. And where's my wave? There's my wave. Okay, so I'm drop some values over here. I don't have to do all of them. No, maybe I do. I better try just in case. And out. Okay, and my 100 nanoseconds there. Okay, I'm running my simulation. I click this run. Now at the point where you're running your simulation, you see there's a simulate here, and choose in simulation. Then you say yes. Alternatively, down here you could type quit space dash sim, and that quits your simulation. Actually, as it bounces forever, it comes back. Get rid of that because it's obviously not working. But again, I could add 5 more variables in here. That's 32 rows. That's 64. That's 128 rows. That's 256 rows. And that's 512, 1024. I wouldn't even want to try to do a truth table that has that many. But with a simulator here, we can easily put whatever we want in. You just have to know the proper syntax. That the two ampersands, two and symbols, is our and, or what appears like multiplication. The prime are not, like not B is done with that little squiggly. And then the or what looks like a plus in our Boolean expressions, is the two pipe symbols like that. Questions on any of that? Okay. Okay, so then you can have multiple assign statements too down here. So it's like you got a variable. You can think of these as variables. You got A, B, and C coming in, and instead of them being like values, they're like voltage coming in. It's gonna be 1 or 0. Your output is E. That's like a variable. It's gonna give you your end result. And then you got the wire D, and we'll talk about the wire D here in a second. Um, then you sign this, and these are just comments down here. The wire. If you look at the schematic for this, we only got 3 inputs. And so D is not actually an input. So you can't say it's an input. These are only ones. Because the inputs are the ones you actually will force voltage, whether it's 1 or 0. A and B are coming into this OR right here. And then it's going to give us a result that we need to send into here. So that's why you need something called a wire as like intermediate variable type of deal. Does that make sense on what the difference is a wire and input? Okay. And this, again, the two little pipe symbols here is our OR. The two ands here is our AND. What do I say that? Pipe symbol is a logical OR operator. I'm almost 100% certain it has to be 2 pipe symbols, but anyway. Okay, let's try to program this. This is on page 125. Okay, so go back to my code here, and I'm trying to program in. Now, what's our inputs into that? Well, our inputs are what's coming in here, A, B, and C. So we got A, B, and C. Our output is going to be Y. So our output will be Y. And we'll assign out equals something. Now, usually it's best to start from the end here instead of the beginning, as weird as that seems. This is an and, so that's like a something and something. Now, coming in here is a D. Now, this is not an input, it's the result that's coming from that. So this would be a wire. So D is coming into that. So right here, I'm going to say D. And what else is coming into that is C. So C is coming in there. Okay, so that's going to accomplish that D and C. Now let's see what the D is coming from. D is coming from this. So I'm going to have an assign here. D, you have to put it before you actually use it in the next one. And we're going to ignore that inverter on the front. The inverter on the front means you just put a little curly bracket in front of it. Actually, let's go ahead and talk about that. That's what that's saying. So you take whatever the result of this is and you invert it. So we have our little curly brace and then whatever's inside. Now what's coming inside is this, which is not A and B. So not A would be this. Now this is coming into an OR. So that'll be an OR with just those 2 pipe symbols and B, B. I'm going to save that, run it, and see how close I am. Or if I got a bunch of errors, probably a bunch of errors. Nope, that worked. Does that make sense how to work into that backwards? Yeah, and they say that somewhere in a book. I don't think I read it, but out loud. But somewhere in the book it talks about you working these backwards. If you work from this side, it's a lot harder to wrap your mind around. Now they did it all in one line here. Oh, they did exclamation. Exclamation is also inversion, I guess. Okay, and C. So they took this and brought it down into the D instead of having a wire in there. I'm not sure if I actually agree with their answer, but we'll go with that. What do you think's wrong with their answer? There's no D. They told us to use D. So they're implying they want us to use a wire. Now, it's probably actually a little bit more efficient not to use D, but since they specifically said that, then they should have. Anyway. I'm going to put some problems out there, but I don't think I'll put a Verilog program out there yet. There's some out of the book that I want to assign. And then I want one more day of working with Verilog at least. Then I think people, everybody, not just you, but everybody in the class will have the knowledge I need to be successful at that. Is there any questions up to that? Yeah, I like this compared to what all the rest of the stuff we've looked at. I like this. I like this stuff. It's a little bit of programming. It's not your standard for while loop and so forth, but I can at least wrap my mind around it. Well, I'll go ahead and stop the recording there, and I'll put the problems out.